Modern horticulture relies on sterile, expensive, synthetic rooting chemicals and mineral salts, yet many industrial root systems remain anemic. This dependency creates a systemic inefficiency where growers attempt to fix biology with static chemical inputs. These synthetic auxins are biologically inert. Once introduced to the soil profile, they degrade rapidly, providing only a brief window of activity before the compounds break down. The alternative is Saccharomyces cerevisiae, common baker's yeast. It is a single-celled fungus that functions as a highly effective, low-cost biological input. This chart displays empirical data from agronomic trials on Mexican maize. The yeast-treated plants achieved a 1.5 times increase in root mass and plant height compared to the synthetic control groups. Agronomic optimization requires more than pouring chemicals into the dirt. It requires engineering a dynamic, localized biological reactor within the soil itself. Cultivating an active yeast colony at the root zone creates a self-replicating bio-stimulant. This living colony provides a continuous biosynthesis of indole-3 acetic acid, cytokinins, and immune-triggering glycopeptides. On the left of this model, synthetic IAA applied to a root passively washes away. On the right, the yeast colony actively multiplies, providing a continuous supply of growth compounds. We will now break down the thermodynamic activation protocol, the specific chemical signaling pathways, and the supply chain physics that prevent this from being sold at retail. Understanding this microbiological cascade allows you to completely bypass expensive synthetic stimulants and rewrite a plant's growth architecture. The in situ bioreactor requires 3 raw inputs: 1 liter of water, 20 grams of dry S. cerevisiae, and a tablespoon of sucrose. The sucrose is not direct plant nutrition. Once the colony begins rapidly dividing, it secretes a high density of plant growth regulators directly into the water solution. The primary hormone produced is indole-3 acetic acid, or IAA. This master chemical messenger instructs root tissues to stretch and initiate aggressive lateral branching. Cytokinins act as the secondary signal. They target the root tips to force rapid cellular multiplication. Fermentation also releases highly bioavailable amino acids, B vitamins, and trace minerals. Unlike granular fertilizers that require microbial breakdown, these outputs are pre-digested biochemical building blocks that allow for instant cellular uptake. This raw concentrate has an extreme osmotic load. Applying it directly will burn fine root hairs and shock the soil microbiome. You must use a 1:10 dilution, 1 part yeast concentrate to 10 parts water, and apply it as a soil drench. This schematic illustrates competitive exclusion. Yeast cells rapidly colonize the root zone, forming a physical barrier that starves out harmful soil pathogens. The yeast also secretes glycopeptide molecules into the soil. These interact with root receptors to trigger systemic acquired resistance, the plant's immune system. The plant operates within a fortified, disease-resistant microbiological shield that enhances nutrient absorption. Weekly application will cause soil dysbiosis. The strategy relies on specific chronobiological timing. The first window is transplantation. Applying during this phase forces explosive root expansion within 48 to 72 hours. The second window is the start of flowering. This builds the massive vascular infrastructure required to support and retain blossoms. The final strike occurs at fruit set. This supports the intense nutrient demand of mass fruit fill. This protocol is effective across various crop profiles, including high-fruiting vegetables like tomatoes and maize. These 3 targeted biological strikes per season will fundamentally rewrite the entire root architecture of the crop, maximizing your end-of-season yield. If this protocol is scientifically validated and costs pennies, why is it absent from commercial agricultural retail? This model shows the thermodynamic barrier. Live yeast continuously produces carbon dioxide and alcohol, causing extreme pressure buildup in a sealed container. Put a living, fermenting biology into a sealed commercial bottle, and the vessel violently fails. The industry business model requires inert mineral salts that can sit in a hot warehouse for 5 years. Living biostimulants break traditional logistics. The retail shelf cannot hold active fermentation, which means it cannot profit from it. Superior yields are achieved by mastering microbiological signaling rather than purchasing expensive dead inputs. The 1.5 times increase in root mass seen in maize studies is a direct result of this localized chemistry. Reaching the full agricultural potential of a crop is a matter of engineering a living, localized biological reactor, not pouring more synthetic chemicals onto the soil.